Hi everyone, I'm Mrs. Holtzman. I teach chemistry and psychology, and I've actually taught Tanay since he was in 6th grade chemistry, and I taught him AP chemistry, and this year he was also my TA, and he asked me to be his senior project advisor. So I've worked with him a lot, and I'm really proud of the work that he's done. I think this is a great project that you guys will all enjoy the presentation of, and I'm so glad that he's working on bettering our Earth and continuing on studying sustainability when he goes off to college. So enjoy the presentation.
Thank you, Ms. Holtzman, for those kind words. Before I start, I just wanted to say thank you to all of you guys in the audience. It truly means a lot to me that all of you are here to watch my presentation. So, a couple years ago, I went to New York City, and one morning when I looked out my hotel window, I couldn't see the sun. And this was because there was thick black smoke in the sky. Now, some of you may have heard this in the news, but also a couple years ago, around the same time that I went to New York City, there were large wildfires in Canada, and this was caused by a rise in global warming. Now, the smoke from those wildfires came into the city of New York, which is why I wasn't able to see the sun that day. And so witnessing such a massive climate event, along with the general rise in global warming around the world here in Phoenix, Arizona, and more disastrous climate events like hurricanes, tornadoes, wildfires, made me start my journey in sustainability and sustainable technologies. Now, I've tried to explore that throughout my high school career, but all of that has led to the culmination, which is my senior research project entitled Optimizing Carbon Dioxide Removal, Enhancing Direct Air Capture, or DAC, through sorbent selection and home implementation. My name is Tanay Naik, and as I said before, I'm very excited to be presenting this project with you all here today. My faculty mentor is Ms. Brittany Holtzman, and my on-site mentor is Mr. Matthew Ryan at the Center for Negative Carbon Emissions at Arizona State University. So to understand my project, we first need to ask the question, what is direct air capture? Basically, with direct air capture, what we're trying to do is removing carbon dioxide from the atmosphere. Now, why do we want to remove carbon dioxide? That's because carbon dioxide is the most prevalent greenhouse gas. And as we know, greenhouse gases cause global warming. So when we remove carbon dioxide, we're decreasing greenhouse gas concentrations, which means we're decreasing global warming. One advantage of direct air capture is that it can be implemented anywhere around the world. And also, something integral to direct air capture are things called sorbents. Sorbents are what capture the carbon dioxide. Here in this figure on the right, you can see that the air goes through a sorbent capture system and the carbon dioxide is filtered out. So what are sorbents? Now, throughout this presentation, I want you all to think of sorbents as sort of like the glue that carbon dioxide sticks to. Because here in this figure, you can see that we have our air with nitrogen and carbon dioxide, but once it passes over the sorbent, only the carbon dioxide sticks to the sorbent. And so since it sort of sticks to the sorbent, that's why I like to call it the glue. Now with my project, I aim to answer 3 main research questions. The first being, can I efficiently remove greenhouse gases from the atmosphere? Then I wanted to ask, can I improve public faith? Can I improve your faith in direct air capture systems? And the last being, can I use DAC as an educational tool for the younger generation? That's because I believe the generation after me will be affected by climate change the most, so it's necessary to educate them about this so then we can provide them with the tools necessary to fight for a better planet. Now with my project, there's 2 main parts. The first is at home and the second is in the lab. With the at home part, I aim to create a low cost, accessible, at home direct air capture unit. I named it Aether after the Greek god of air. And the second part is in the lab at the Center for Negative Carbon Emissions at Arizona State University, where I wanted to look at scaled up high-tech direct air capture technologies in that lab. So first to talk about the at-home part with Aether. Now some past research is that in 2019 there was a company called Open Air which released a at-home DAC unit called Cyan. Now Cyan was able to capture a 1:5 ratio, 1 gram of carbon dioxide for 5 grams of sorbent. So the main question that I had with Aether was, can I improve this ratio? Can I make this better? So how did I do this? The first was to create a list of necessary materials. You can see on the left there, you can see like plastic boxes, coffee filters, aquarium air tubing. These are things that you can find at Walmart for less than $50 in total. The second step was to build Aether. Here in this picture on the right, you can see me sort of sawing into the box, trying to make holes in the box for wiring and airflow. You can also see Aether out in the lobby, and you can view all of these things after the presentation. The third step was to examine a list of potential sorbents. My faculty mentor, Ms. Brittany Holtzman, graciously gave me a list of 127 potential sorbents that were available here at Basis Phoenix. And so I went through each and every one of them, and then you can see there's 8 here, but I examined each of them basically to see, can they even capture carbon dioxide, and if they're even safe for human use. So my last step was to conduct multiple tests, and you can see me in this picture here weighing out the sorbent. Now, I'll show you an animation in a couple minutes of how Aether actually works, but I want to highlight the main chemical reaction here on the top. We have our calcium hydroxide, the sorbent, the glue, that reacts with the carbon dioxide to create calcium carbonate. Now, the intriguing thing about calcium carbonate is that it can be used in gardening to improve the quality of plant soil. So what this means is that we create a carbon neutral loop with this reaction. Now, to go into this animation here, the colored dots represent nitrogen, oxygen, argon, and carbon dioxide. This is what's naturally found in the air we're breathing right now. Then this white block in the middle here is our calcium hydroxide sorbent, the glue, as I've said before. And over time, what happens is that carbon dioxide reacts with the calcium hydroxide sorbent, and it turns into our calcium carbonate. These green dots you can see here. Now, what I want you to take away from this is that some of the sorbent remains unreacted, while some of it turns into calcium carbonate. That's very interesting, and I'll talk about that later. But here you can see a general schematic of Aether. We have our fan, which is blowing air into the unit or outside of the unit. Then we have our air pump, which is blowing air into the water. What happens there is that we create bubbles, and the carbon dioxide in these bubbles is then able to react with the sorbent, which is resting on a lid platform. So with Aether, there were a lot of challenges, the first being the air tubing. Our air tubing was almost 6 feet in length, and the box is like less than a foot, so I needed to make sure that I cut it to a good enough size that I could optimize airflow. The second thing was the air pump. The air pump, midway through the build, just stopped working, so I had to take it apart and look at the electronics behind it. Fortunately, it was just a manufacturer's default, and I could just go to Walmart and get a new one. The last thing is the corrosive potential with the cream cheese container. Yes, you heard that right. All the way, the figure on the left is jalapeno salsa cream cheese from Einstein Bros Bagels. Now, while this was very delicious to eat, this could pose a very dangerous threat to our experiment. Why? Because this lid is actually too small. In the figure all the way on the right here, you can sort of see the coffee filter, which the sorbent is resting on, is actually dipping into the water. Now, this is dangerous because our sorbent is a strong base, meaning if it mixes with water, that water turns corrosive. It can burn your hand with just a drop. And so that's why this was very dangerous. So I eventually had to swap this lid with a large container lid, which was actually Ms. Holtzman's lunch container lid, in the spirit of making Aether as accessible as possible. And so, however, fortunately, what happened is that the sorbent actually did not end up mixing into the water, which was, thankfully, it did not become corrosive, but that's why we had to change the lid. So here are my main results. I did a lot of runs, but I wanted to highlight these 5. For the first run, we just kept the sorbent out on a table to see how much it would capture over 24 hours, and we captured a ratio of 0.1 to 5. For the second run with the cream cheese lid, we captured a ratio of 1.3 to 5. So we are already meeting past research. Now with our third run, we switched it to Ms. Holtzman's large lunch container lid, and we were able to capture a ratio of 0.95, so a little bit lower than the previous run. Now our fourth run is very intriguing because, as you can see here, we captured a ratio of 3.2 to 5. Now this is more than triple past research, so this is a great achievement, a great success for Aether because we were able to triple what past research did. The thing with this is that we changed the fan's directionality. Instead of blowing air out of the box, we started blowing air into the box. And I think that because of this improved airflow, we were able to capture so much. Now for our fifth run, we introduced smoke. This was actually rose-scented incense sticks. It made Ms. Holtzman's classroom smell somewhat nice. And we ran that for only 2 hours, and we were able to still capture 0.6 grams for 5 grams of carbon dioxide, So what Run 5 basically shows is that in areas of high pollution or areas that have recently been hit by wildfires, Aether can sort of provide relief for households that are in areas of high pollution. So it shows that Aether can be used in these areas as well. Now, what do these results mean? The first is that when we have higher CO2 concentration, we have a higher rate of capture. We saw that with our 5th run with the smoke. When we introduced smoke, we were able to capture 0.6 grams in only 2 hours, which was really great. However, the second conclusion is that it's something very interesting, which I like to call the saturation hypothesis. I'll show you another animation here. So this is a side view of the sorbent. We have our carbon dioxide surrounding the sorbent. Now watch what happens. As usual, our carbon dioxide reacts with the sorbent and it creates calcium carbonate. But what you may recognize is that the middle layer, this inside layer of sorbent, is not being exposed to the carbon dioxide. That's because this whole outer layer is saturated. So that inner layer is just sitting there and it's just sort of not doing anything. So we sort of see this graph here where for the first couple of hours we see a massive rise in grams of carbon dioxide captured, but then over time that becomes saturated and the curve flattens out. Now to analyze on this entire experience, the possible sources of error could include the fluctuating mass balance. This was because the experimental setup was directly under Ms. Holtzman's classroom's AC. So the wind from that AC caused the coffee filter, which the sorbent was on, to sort of flap in the wind. And because that happened, our mass balance read like 0.1 grams or 0.2 grams, and it kept on changing every second, which could have led to some error. The second is timing variations. We wanted to run each cycle for 24 hours exactly, but just because of general human occurrences, we ran it for like 24 hours and 30 minutes, 24 hours and 15 minutes. So that could have changed things as well. The last is different thickness. Once again, with the saturation, for different runs, we sort of had, one time we had the sorbent clumped up in the middle, but then sometimes we had the sorbent spread really thin on the coffee filter. And so because this happened, the differing thicknesses of the sorbent could have influenced the capture rates. Now, something I want to improve in the future is definitely test different temperatures, like hot water, cold water in the system, to see if that makes us capture more carbon dioxide or not. Now, to reflect on Aether, I had to do a lot of thinking outside of the box, both figuratively and literally. I faced a lot of challenges, and to overcome those challenges, I believe really enhanced my experience and made me learn a lot through them. Also, I want to point out that Aether can be used as a tool for education and advocacy. A couple weeks ago, I was a camp counselor at a 3-day overnight climate camp, where in one of the workshops, I was able to teach middle school children about direct air capture, and they became really excited about it, so that's why I believe we can use it as a tool for education and advocacy. Additionally, I think in the future we can sort of ship out these Aether units as sort of mini kits that children can build at home for themselves, obviously with a much safer sorbent, but so they can be exposed to climate technologies at a young age so we can get more people behind this issue. Now, at this point in my project, I asked myself a question, and I said, what if we scaled up Aether? What if we took it to the next level? What if we used high-tech industrial level DAC, which that next level was at the Center for Negative Carbon Emissions at Arizona State University. Now, this is scaled up high-tech industrial level DAC because I wanted to see if I can make a difference at this level. So my experience in this revolved around one machine called Sapling. This was thermal swing direct air capture. What this means is that at room temperature, we capture carbon dioxide, but then when it's hot, we release the carbon dioxide. Now, you may ask, why do we want to release the carbon dioxide? That's because we have two reasons. The first is that once we release the carbon dioxide, we can store it and we can ship it off to other chemical factories. So once again, we create a carbon neutral loop. But the second reason is that when we release that carbon dioxide, we can keep on reusing the sorbent so we don't have to remake it every single time. So this, once again, is very good for the environment. Now, some challenges with this whole experience were there were lots of leaks and there was lots of sensors that I needed to calibrate. And so overcoming these challenges also, once again, enhanced my experience. You can see here in the figure on the right, I'm trying to fix a leak in the tubing. Now here's some images of me in the lab. You can see some wires in the top left here, some soldering attempts. I had to also learn how to solder. You can see me loading up the sorbent on a ladder here into the sapling. These are some sorbent cassettes, and once again, you can see me here trying to fix some leaks and do some sensor calibration. Now here's yet another animation, but this time this is about how sapling works. We have once again our air surrounding our sorbent. Now over time, what we see is that the carbon dioxide settles into these sort of pores. The main difference between the sorbent and aether and the sorbent and sapling is that in sapling, the sorbent is sort of like pores or like holes. I want you to think of them as sort of like golf balls going into their golf holes. And so that's why you can see this carbon dioxide is settling into these sort of pores here. And it's not entirely reacting with the sorbent. Then what we do is we use vacuum. So we basically just pull all the other air out of the system. So that moves out. And then what we do is we introduce some steam that is less than 100 degrees Celsius. Now you might know that water boils and we make steam at 100 degrees Celsius. So how can we produce steam at less than 100 degrees Celsius? That's because since we are pulling vacuum, that means the boiling point of water drops drastically. That's why we're able to introduce less than 100 degrees steam. But anyways, once we introduce that heat, the carbon dioxide gets released from the sorbent, and then we pull it through our carbon dioxide sensor, once again through vacuum, and then we can see exactly how many grams of carbon dioxide we've captured. So my original methodology actually changed a lot. I wanted to originally examine many different types of sorbents in many different machines, but because of time constraints, I was only able to examine 2 sorbents in one machine, which is the sapling. So my methodology eventually became how much carbon dioxide is regenerated by sorbent CR20 at different temperatures, and then how much carbon dioxide is regenerated with sorbent CT20 at different temperatures. Now you may be asking, what is carbon dioxide regeneration? Once again, this is where we release the carbon dioxide from the sorbent, and we release these for 2 main reasons. Once again, the first reason is that once we release the carbon dioxide from the sorbent, we can store it and we can sell it off to other chemical factories, so we create a carbon neutral loop. But the second reason is that once we release the carbon dioxide from the sorbent, we can reuse that sorbent for multiple cycles, so we don't have to keep on making new sorbent every single time. Now, with CR20, you can see the results here. We tested each sorbent at 40 degrees Celsius, 60 degrees Celsius, and 93 degrees Celsius. We saw that CR20 in general performed better than CT20 overall, but what's intriguing about CT20 is that at 93 degrees Celsius, we didn't let the steam actually hit the sorbent, and even though we didn't introduce actual steam for that 93 degrees Celsius, for the first 20 minutes actually, we were able to capture 0.5 grams of sorbent without any heat. So what that means is that we can still capture and release carbon dioxide without heat, which means we can save energy in the future. That's why CT20 highlights something very interesting that I hope to study in the following weeks after this project, but also over the summer and in college as well. So for the analysis, there was lots of error as well with this sapling. The first was that each experiment was conducted at different pressures, and so that could have affected my equations and calculations. Small leaks may also still exist. As I mentioned before, we're using vacuum, so what that means is that we don't want excess air, outside air, coming into the system. And the last error could be computational error. Now here you can see around 20 lines of data, but there were around 60,000 lines of data in total, and to analyze each one of these lines could have definitely led to some sort of computational error on my part. Now to reflect on aether and sapling and just the whole experience in general, there was a lot of thinking outside of the box that I did with sapling as well, especially with learning how to use the vacuum, learning how to solder, learning how to use the pipes and valves and air tubing and things like that. Definitely enhanced my experience a lot more, and it challenged me, and I'm honestly just grateful that those challenges actually happened, because it just made the experience a lot more rewarding when we got results at the end. And this is why I also hope to continue developing direct air capture technology in the future. I'm also going to be working after the senior project in the lab in the following couple of weeks, but also in college and over the summer as well. Now, what I want you all to think about now is, what if we combined aether's accessibility, the fact that it's so low cost, with sapling's groundbreaking technology? Then we may be able to imagine a future where every single household has their own aether unit. So here were my works cited. I'd like to say thank you quickly to Basis Ed, Basis Phoenix, Miss Layton, Miss Bennett, Miss Rothschild, who gave me the opportunity to conduct a project that I'm very passionate about. Also, thank you to Miss Brittany Holtzman for all her time, guidance, support, and letting me run experiments in her classroom, especially with using her lunch container lid. She definitely won't be eating lunch out of that anymore. But thank you to her for all of that. Thank you also to Mr. Matthew Ryan. He personally took countless hours in the lab to train me on sapling so that I would be able to use it independently. And like for 3 weeks straight, we literally worked like a 9 to 5 in the lab, and so I couldn't have done it without him. Also to Dr. Matthew Green, the director of the Center for Negative Carbon Emissions at Arizona State University. He started the paperwork to allow me to work in the lab, so thank you to him. And last but not least to my parents, who allowed me to use their car to commute to ASU every day. I definitely could not have done it without them. Now, you saw these 2 quotes at first slide, and that's because I wanted you all to look through my presentation through the lens of these 2 quotes. Now, I want to be honest with you all here. Aether is not the only solution to climate change, and sapling is also not the only solution to climate change. In my opinion, there will never only be one solution to climate change. It will take thousands of different projects working simultaneously in collaboration to solve a problem of this magnitude. And that's why I want you to think of Aether as an educational tool. The fact that Aether is less than $50 means that it can be implemented in any high school, any middle school, any elementary school, even in the most under-resourced school districts, even in the most developing countries all around the world. That means we get more students and more children who are more interested in climate technologies, sustainability, and working towards solving this problem. Because what we need is more climate scientists, more researchers, more thinkers, more people to question this problem and develop projects to address these. Because, as I said, as the first quote says, we need to take matters into our own hands. And as the second quote says, if millions of people do this, if millions of Aether units are developed all across the world, then truly we can transform the world. Thank you.
Thank you so much, Tanay. I will open it up for some questions. I know it's the end of the period, or we're nearing the end of that, so if there is any questions from the audience, I'll try to catch those. I see when all the
We frankly didn't have that much of it in our Basis Phoenix laboratory, and that's why I didn't use it for my project, but that's actually a more safer sorbent than calcium hydroxide. So I would definitely look at that first and see if we can use that.
Thank you. We'll take one last question in the back, and then we'll wrap up.
You mentioned that the calcium carbonate was useful because it was carbon neutral and you could use it for art. I was wondering if you had prototyped or done any work on trying to come up with a system similar to sapling, how you extracted the products of the chemical reaction and how you'd be able to actually use that in your Aether unit.
Yeah, so for sapling, sort of the difference, the thing is in Aether, the sorbent undergoes a chemical reaction from calcium hydroxide to calcium carbonate, but in sapling, the sorbent stays essentially the same after the reaction. So we just keep on reusing the sorbent, and then we store the carbon dioxide to ship it off to other chemical processes.
One last round of applause for Tanay. Thank you so much.
Thank you.